So is my screen visible? Okay.
Yes, ma'am, it is visible, ma'am.
Yeah. Good afternoon.
Can we check with that slide changing, ma'am? Yes, ma'am, it is changing, ma'am. Sorry to interrupt you, ma'am. Thank you.
No issue, sir. Thank you. Good afternoon, everyone. I am Barni Rajagopal. So I'll be covering on the topic fuse deposition modeling, technology, variance, and research horizon. So this is a 1.5 hour session. So it would be much useful and entertaining if everyone could contribute or everyone could pitch in with the discussion. Because all of us are researchers and we should collaborate basically. So let me begin. When I say 3D printing, when everyone hears the word 3D printing, especially FDM printers, what they actually visualize are toys. Okay, mostly the Peggy toys, the Lego toys, only that will come into mind. But right now, many aerospace industries, in particular Airbus, they are printing FDM print. They are using FDM printed components in that Airbus. Or consider implant. Many doctors, they are actually giving the print in the morning. Okay, based upon the patient specific data, they are giving the print in the morning, and by the end of the day, they are actually using that implant print, and they are keeping it inside the patient body. Or researchers are actually printing live cells for research purposes, and even different sectors, they are using lots of unmanned robots or unmanned aerial vehicles, which are also 3D printed or FDM printed in specific. Okay? So we are going to see in detail about these applications and where the research can move and how we can progress in that particular domain. So before going into the slide, can anyone share whether they have actually printed a component in a desktop FDM printer? Have anyone printed anything? It can be as small as a wire holder, or it can be as big as an implant. Can anyone share? You can also message. Have anyone used 3D printers? Is this tab also visible in the presentation?
Yes, ma'am, it is visible, ma'am.
Okay.
Yes, you can close that tab, ma'am.
Yeah. Can anyone share whether they have actually used it or not?
Yes, ma'am, in our institution, we are using it, ma'am.
Super, sir. So what application? Have you printed any component? Can you share about that?
Research level samples we have printed, ma'am, with ADX 5X printer.
5X, okay. Okay, so for what component?
Like tensile test for research work we have done it, ma'am.
You have incorporated different materials and you have characterized those materials. Yeah. The material science, that is a very, very big field in 3D printing, especially in FDM, because we are trying, all would have known that FDM is only known for thermoplastic printing, right? So a lot of research is currently being done to bringing other engineering components that can be printed. I think Arvind Ratsa's project, PhD project is mainly in metal 3D printing, metal FDM printing, right? So your PhD is about that only, right? Okay. So let me start with my presentation. So I'll be giving you an overview of what is FDM, the variants of FDM, like how different engineering materials can be printed using FDM. Then I will be sharing some, in between I'll be sharing my research areas, what we have done using a FDM printer. Then I will be closing off with what are the research possibilities, what are the challenges, and what future PhDs can focus on. So before understanding the significance of additive manufacturing, let us see the evolution of manufacturing. So it all began with the lathe machine. It was a subtractive technology. We actually removed the material. It was labor intensive and it's completely dependent on the skill of the labor. Then we moved on to less labor intensive, that is we tried to program it. That's where the CAD/CAM and CNC came. With that evolved the 3D printing, that is additive manufacturing, where without removing the material, we are building it layer by layer. So with 3D printing also evolved the industry 4.0, where the machines were joined together or machines were connected using IoT, data cloud, that resulted in smart manufacturing systems. Right now we are in this industry 4.0. I can give a lot of examples like BMW collaborative robots. Okay, the robots are in between us. using the humanoid robots, they are actually assembling the BMW cars. Next comes the evolution, that is Industry 5.0, where human will be in the center of the connected missions. So this is more like a collaboration between the human and the robots. So that is where we are heading. So for this Industry 5.0, additive manufacturing plays the key role. Okay. So till now, actually what we have done is we actually moved from mass production. So everything we had, let us say using lathe or CNC, it was all mass production. Then came the 2020, 2010s and 2020 where customization was preferred, patient specific or customer specific products. That was the focus. Now we are moving towards the mass customization. Yes, we are customized. Now I'm going to produce that customized product in a mass production rate. Okay, that is where we are heading. So that is all about the Industry 5.0, where we are trying to integrate human with the machining sector. So that is where the 3D printing, digital twin, everything comes into play. Any idea about digital twin? Have you heard this term? You can also comment in the message section. Have you heard this term, digital twin? Okay. I think you had a session on digital twin. So digital twin is also a very, very important research domain in case of additive manufacturing. We'll see that in detail. Yeah, so why is everyone talking about 3D printing? So from traditional manufacturing, that is subtractive, we have actually moved on to the additive manufacturing sector. So in subtractive, we will be removing layer by layer. We'll be removing the material and we'll be creating a final product. So we'll be having a billet. From the billet, I will be converting that into a shaft of my required shape and size. Whereas in additive manufacturing, I'll be adding it layer by layer so that any complex object can be printed and material wastage will be near zero here. So this AM additive manufacturing has a huge global market. By 2030, we are expecting it to generate about $66.7 million. So it is growing at an annual rate of 20.1%. I wish my personal finance portfolio grows at this way. So it's creating a huge demand. And most of the industries, that is medical, aerospace, automotive, construction, energy, and food, they are contributing to this revenue. So out of these sectors, which sector do you think is contributing the higher? Medical, aerospace, automotive, construction, energy, or food? Please let us make it more interactive. Otherwise, it will be very boring. It's an afternoon session, and we would all had a good meal. So it's a simple question. Which sector do you think is contributing most to the revenue? Pin drop silence. Medical sector. Yeah, medical sector comes second. The first one is actually the aerospace. Aerospace is actually contributing the highest. Then comes the medical field, because as you know, aerospace recently, even the private aerospace companies are coming up, like Godrej Aerospace Research Centers. So they are actually contributing the highest. Then comes the medical field, and then comes the automotive sectors. The remaining three sectors, the construction, food, and energy, they are actually contributing very less value. But these three sectors are rising sectors. So if you do research in these particular sectors, your problem will be identified and can be easily published. Right. So what is additive manufacturing and how do you do it? So basically, we'll be having a CAD model, and from the CAD model, we'll be converting into an STL file. Can anyone tell me what is STL? Can anyone point out what is an STL? And what is the difference between CAD and STL? Let me connect via phone so that I can check your messages also. Yeah, stereo. Stereolithography. Just a second. Stereolithography. Okay, so since SLS was the first 3D printer that came into market, so the converter, the in between data is actually represented as STL file, stereolithography. Okay, I have a question. Why do we need a STL file? Why can't we directly print a CAD model? That machine is going to read a data, right? So why can't it directly read a CAD data and directly print it? Why do we actually need an STL file? What is an STL file? What actually happens there? What actually happens there? Why can't I print a CAD file? Okay, so basically a CAD file is a geometric file. It contains the geometric data as in the origin or the dimensions, like the 3 points, that is X, Y, Z data. But what the machine actually needs is where it should move from one point to another. It needs a coordinates, right? So for that, what happens is the CAD file, it breaks down from the CAD file, I'm converting into STL model where the geometric data is broken down into lot of triangles. Okay, when you convert, when you say, for example, you're working on SolidWorks and you're converting that solid profile into a STL file, means what actually happens is the entire data is now converted into small triangles. Okay, so that is the purpose of STL. Once those small triangles has been converted, then we'll be using a slicing software to slice that model, solid model into layers. Okay, so for that we also require a slicing software. Then this slicing software is then slicing G code is then given to the machine where it will be printing layer by layer. Okay, so why we actually can't directly print the CAD model is another reason is we actually require some supports. Okay, only after slicing it you can get an idea as in where the supports has to be needed, right? So that part, the slicing part, is where the G code is created for not only producing the part but also producing the supporting material also, right? So once we print it, then we let it cool it, then we actually remove the support, then do some post-processing techniques, like if it's metal, then it will be sintering it, then it will be curing it. Okay, if it is FDM, we just remove the supports and then the material is ready to use. So this is a basic additive manufacturing process. There are actually ASME has classified additive manufacturing as 7 techniques, so I'm not going to go much in detail about it. I'm just going to give a brief overview. So what we are going to focus today is about material extrusion. Okay, so a filament will be inserted into the nozzle, it will be heated, and then it will be pulled out, and layer by layer will be building it. Okay, so can you give some product examples for material extrusion? What product can be done in material extrusion technique? Raman sir, yeah, you are actually replying for my questions. What products do you think can be produced using material extrusion? Okay, let it invert it. I will give you some product example. Tell me which technique will be used to produce it. Dental aligners. Okay, I have a dental aligners. Which technique do you think can produce dental aligners? We think like it. Dental aligners are made of resins. Okay, if you go to a dentist to straighten your teeth, okay, straighten your teeth profile, then you will be using resins, right? So which machine can print resin? Come on, guys. I've given a lot of clues. Which machine do you think can print resin? Yeah, the first 3D printer that was found, it is SLA, stereolithography. Okay, that is VAT polymerization. We have resin. So that resin can be printed using VAT polymerization. So you'll be depositing resin layer by layer, and it will be cured using a UV light, right? That is VAT polymerization. So VAT polymerization basically is used to print resins, and it has major application in dental industries and jewelries that prototypes can be made. Before it was actually investment casting was used to do the wax prototypes, but right now they are using that polymerization to make the jewelries. How about ceramics? Yeah, Muthukumar sir. Yeah, FDM and SLA. Yeah, great. How about ceramics? Out of all these missions, which one do you think will build ceramic? Ceramic or terracotta, any clay. Which mission out of this can print a clay? Someone has to answer, otherwise I'm not moving. Which mission out of all these 10 types do you think can print clay? It can be a ceramic or it can be a terracotta. Right. Binder jetting. That technology can be used to make a ceramic or a terracotta, etc. Okay. You can also build a sand casted products using binder jetting. Okay. So there are different materials like ceramics, terracotta, composites. Okay. So machining a composite also we require SLS, selective laser sintering. Right. So depending upon the material, different technologies are being used to make the products. Right. So why I'm focusing about FDM? So FDM is actually the most affordable 3D printer across all the 7 technologies. Right. So it is affordable. It is actually very simple to use, easy to operate. So that is the reason why I'm talking about FDM, because many of us as a researcher, we would have a huge drawback in funding. Right. So it is very simple, and using this FDM, we can actually have a lot of research opportunities. We'll see what are the variants and what are the products developed using those variants. Yeah. First, the FDM was actually developed as a prototyping tool, right? So if you want to visualize some complicated product before going into manufacturing, if you want to visualize and if you want to see whether it is going to work, if you want to make sure that there is no failure, then that is the first application of an FDM. It was developed as a rapid prototyper. Okay, for example, the Kaveri engine. So Kaveri engine was, the mission was started in 1980s. It is a very complicated first in-house. This engine was the first engine that was developed in India for rocket launching. So here we have nearly 2,500 FDM printed parts that have been assembled. Look at it, so complicated. The objective for FDM printing, it is actually prototype. That it is not a real engine. The objective for this printing this is because it has lot of internal channels and lot of line replaceable units. Okay, so this cannot be visualized using a normal CAD software. So for overcoming the drawback only, it was actually FDM printed. Instead of FDM, you could have also machined it using CNC, but it would have taken nearly 12 months, whereas using FDM printer, it was down to 6 weeks. So it is very, very easier tool for visualizing whatever product you're going to print. Before manufacturing, you can actually visualize it, how it is going to look. Yeah. Next, I want to talk about the defense sector. That is, what are the robots that are being used in DRDO. So these 3 robots were developed by DRDO. So this is a miniature unmanned ground vehicle. So it is a tracked locomotive. Any idea what is a tracked locomotion is? Can anyone suggest what is a tracked locomotion is? Can anyone suggest what is a tracked locomotion? The benefit of this is because this robot can actually negotiate between the rough terrain and staircases. So tracked locomotion is you don't have a single wheel, you have actuating. Your actuator will be a chain or a belt. Okay, so that type of robots are said to be tracked locomotion robots. Okay, so this is actually fully FDM printed. The main body, that is the black color, the main body is ABS, and the movement, that is the locomotion part, is printed using TPU. TPU will be it will be like a rubbery. It will have a good strength with the rubbery texture. So that is used. The white part is TPU, and the main body, the black part, is ABS. So this is completely FDM printed component. Similarly, you have this snake robot. Just imagine if you are going to build this using a conventional technique, how many joints, how many rigids, how many links you have to use. There will be lots of links, joints, and rigid bodies you require. But when this is going to be FDM printed, we are going to use a different anatomy. We are actually inspired by the snake anatomy. This particular robot has been printed. So the thousands of joints and links has been produced to few hundreds. That is the biggest advantage of FDM. Here the body is actually made up of ABS and the joint connectors are made up of PETG. The black one is PETG and the white one is ABS. And next we have the Omni Hexabot. So this robot is also 6-legged and it can move in any direction. I'm not talking about the mechanism or how it is being built. What I'm saying is, if this is being done in a conventional method, it would have taken a lots of design iterations. Like you will be having thousands of joints, rigid bodies, and thousands of links. Instead of that, it has been reduced to just a few hundreds. Right. So this is one important research domain in FDM. This is actually a porcospinoflex. Okay, this is a robot that combines the advantage of porcupine's defense mechanism, that is quilling body, with the flexibility of a vertebrate. So this is a millipede and this is a porcupine. So by combining both are both of bio designs, we are actually generating a robot. This is a research work, published research work, right? So what actually happens here is, this vertebrae, instead of having multiple rigid bodies, joints, and links, this single vertebrae, inspired by the millipede vertebra, they are actually designed this, right? So this can move and it can bend up to 120 degrees. Instead of having multiple joints, this is a single print. It has a single print. It's a single FDM printed body that is made. This is made up of ABS. Okay. So then over this vertebrae, they are actually mounting two lateral supports. Okay, I can show you it clearly. So there are two lateral supports. So this is a single vertebrae and two lateral supports. And around this entire assembly, they have built a quill-like setup so that it can move in any rough terrain, any unknown terrain. Okay. So this black color, that is actually TPU, right? And this white color, it can be any, it is a ABS polymer. So this robot can move across any unknown terrain, any rough terrain, because of this quill-like structure inspired from the porcupine. This design is from porcupine. It can move across any unknown terrain. And the vertebral design that inspired from the millipede, it actually enables to move freedom, move in a much better manner. That is, it can bend up to 120 degrees. Okay, so this is the first research focus I want to talk about. The bio-inspired contours. There are a lot of applications. If you have some particular problem, for example, I want to create a cutter for aquaweeds, right? So that cutter aquaweeds, actually that was one of our research area. So that cutter can be inspired from an insect, for example, an ant or a locust. Okay, we can get the contour, this contour, instead of having the traditional serrations, we can have a contour like this profile and we can develop a cutter, right? Imagine a dragonfly. So dragonfly has a lot of serrations on the wings. Okay, so these serrations actually make the dragonfly to fly easier, right? So this serration can be used to build a wind turbine. Okay, in your blade, wind turbine blade, you can actually create these kind of serrations so that they have a much lesser drag and they have a good lift force. Okay, so inspired by these kind of bioorganisms, we can actually change our problem to include these contours. With FDM or with additive manufacturing, there is a big advantage. We can actually print any complex contours. Complexity is free here. Okay, the complexity is actually can be done using FDMs. Okay, this is one of my research area. So we had actually published this in a emerging SCI journal, Sadhana journal. It's a B student project. We actually had a problem. Like we wanted to build a micro turbine. That micro turbine should generate power in even a urban or a suburban area where the wind speed will be very, very low. That was our problem statement. My students were very much interested in renewable energy. So they wanted to build a micro turbine, wind turbine that can generate power even at a low speed of 4 to 7 meter per second. So that is where we started to thinking about the bio-inspired designs. How we can have a good lift force with a very, very minimal drag at this kind of low wind energy. Because as you know, turbine requires somewhat at least 12 to 20 meter per second wind speed. That is why most of the wind turbines are kept in windy area like Theni or in those areas. But if you're gonna generate power in a suburban area, how we can do that? So we had some bio-inspired ideas. The first one was Archimedes spiral. So this spiral was inspired by this lotus seed, the Fibonacci seed. Okay, so based on this bio design, we actually created this Archimedes spiral blade. Then we had the Savonius blade. So this blade is inspired by the leaf structures. Then we had an aerofoil. This is a basic aerofoil profile. But in this aerofoil, we actually include the turbucils. So this turbucils was inspired by the shark. Because wind is nothing but a fluid similar to the seawater, right? So how the shark turbucils actually enable higher lift force and reduce the drag force. So based on that technology, based on that concept, we used the airfoil with the turbucles on its leading edges. So our study, it was a very, very simple project. The total cost of this project was only 1,500. We actually made everything in-house. We had a FDM printer. This is a basic PLA filament. The component is the material is PLA. We actually built our own open tunnel setup. So this tunnel setup was used to measure how much of power or electricity it is generating. So from our result, we found that this Archimedes spiral, this had the lowest cut-in speed. It started to generate power at a very, very low speed of 5.8 meter per second. Okay, but the power generated was very less. That is 0.4 watt. We generated 0.4 watt at 5.8 meter per second. But what I'm trying to say is this: installing this micro turbine at the rooftops, it will create an opportunity. So we can generate power even at a low power. This turbine, this profile can generate at 5.8 meter per second. Similarly, Savonius, this profile actually had the highest power generator. So it generated nearly 1.272 watt, but it had a cut-in speed of 8 meter per second. And the last one, aerofoil profile, it had a cut-in speed of 9 meter per second, and it produced a very, very low power input, that is low power output, that is 0.36. Okay, so we actually built it and we tested it in our college rooftop. But the thing is, it was in a very, very micro scale level. The blade profile was around 80 mm only. The diameter of the entire profile was 80 mm. So we had a difficulty in getting paper published. So we actually moved on to numerical experimentation, numerical analysis as well. Because if you are going to publish your paper only with the experimental work, the chances are very, very less. You have to have some numerical investigations to support it so that your paper can be easily published. So what we did is we did some CFD analysis. We did some pressure contour and velocity contouring. So to justify why the profile is creating a lesser drag and increasing the lift. We also did some velocity analysis. We found why the stall is being reduced in these kind of sectors. Why the tubicles are creating a lot of micro vortices so as to increase the power. So like that, we did some analysis. Only with the numerical analysis, they are able to publish this paper. Because if you send this work, what they will imagine is it's like just a toy. What is this? It's a toy created by a third grade or fourth grade people. So whenever you are doing FDM manufacturing, all your prototypes will finally look like just a toy. So you have to have some numerical investigation done in parallel to that so that your paper can get easily published. Yeah, so this is the last work we done, bionic wheat cutter. As I was saying, our problem, begin with the problem, that will be much better. So our problem, this was done for Niral Thiruvala. Our problem was we have to develop a aquatic wheat cutter. Okay, so it should be biodegradable. We don't want to pollute it further. So what we actually made is, we were very sure it should be a PLA material. because PA is biodegradable. It is, even if the cutter breaks down inside the lake or whatever aquatic area you're going to use, it should not further pollute the area. So we were clear about PLA, but the PLA material is not stiffer enough. It will not create enough shear stress to cut the aquatic weed. So what we did is we actually used a carbon fiber reinforced PLA and glass fiber reinforced PLA, so that we have enough shear stress. So, and the next thing was we wanted to have some bio-inspired design. So what we did is we took up two bioorganism, that is we had ant and locust. We focused on the ant's mandible. We took a picture of an ant mandible. It is available, like you can check in the internet. You can see a lot of SEM images or optical microscope images of those kind of mandibles. Once you take that mandible into SolidWorks, you can actually trace the mandible. Okay, you after importing it, you can actually draw over it, trace it, and take that contour into the SolidWorks. So once you have imported that contour, you can convert that into any profile you require. So we actually traced the contour. This was the profile of the ant mandible. Then we build a 3D cutter based on this. You can have a lot of investigation as in what should be the number of cutters, or it should be a circular rotating cutter, or it can be have any other mechanism. So we stop with the 3 number of cutters, but we can also have a investigation. You can actually numerically investigate what is the optimal number of cutters to be included in a one particular blade, right? So we had 3 cutters and a circular cutter. So this is ant mandible based cutter. Similarly, we build another cutter that is based on locust. We took in a locust mandible, drew it over the contours, then imported into SolidWorks, and we actually build a cutter based on the locust. Okay. Then we did a explicit dynamic analysis whether this cutter is strong enough to break the aquatic weed. So we did some numerical investigations. Based on that, we actually determined which will be better profile for the weed cutter. Any idea which one do you think would be a better profile, ant or locust? Okay, at least I should know that someone is listening, right? Or I'm talking to a blank screen. Which one do you think for training purpose? No, what I'm asking is, which one do you think will be better cutter, ant or a locust? So I've taken the profile of ant mandible and locust mandible and created a cutter. So which one do you think would have performed better for cutting the cutter? Second one, the locust. Okay. Actually, both had a good profile. They have both performed well. The thing is, ant actually had a clear cut. When we simulated using explicit dynamic, the weed was cleanly cut by ant profile. It is a clearly a cutter. Whereas locust, it is a shredder. Actually, what it is, when the locust cutter was in contact with the weed, what happened is the weed was split into multiple particles. It is actually shredder. Okay, so we thought we should have a cutter which has a composite, which has both this phenomenon, that is ant as well as locust. So we had we built a shaft, and over the shaft we actually assembled. We had ant cutter, then locust cutter, ant cutter, locust cutter. Like that, we had a combination of 6 cutters. So when we did analysis on that, that was a better performer, because not only cutting it, because if it clearly cut means what happened is that aquatic weed can multiply, because even when cut, it will be left in the water. So it will be multiplying again. It will actually proliferate again. So what we wanted to do was, after cutting it, it should be shredded. So locust will be doing the shredding activity. So we finally thought to design a particular cutter which will be combining both the ant as well as the locust part. So this is still a work in progress. That is why I'm not showing my more results. So what we actually done here is, so this is not only restricted to cutter. If you are interested in any problem in a particular domain, see which particular bioorganism is performing well in that particular domain. For example, as I was saying, dragonfly's wing that has a serration that is very beautiful serrations. If you are able to get that serration onto your wind turbine blade, okay, if you are able to manufacture that profile onto your wind turbine blade, what happens is your wind turbine is going to have a very low cut-in speed and it can reduce the drag in a very good manner. Okay, so depending upon your problem, think of a bioorganism, try to copy that contour onto your own profile, and voila, you have a very good result. As I was saying, don't stop with printing alone, because at the end of the day, when you show that result to a research paper publication, all they're going to comment is it looks very small, because this blade is actually 120 mm in diameter. So what they're going to say is this very small, it's looking tall like a toy. Okay, always support your built prototype with a numerical analysis. Only then you can have a good research. Yeah. The second focus, the materials. Okay, so whatever I have done till now, it was on PLA. First, that the blade was produced using PLA, and the cutter was produced using carbon fiber and glass fiber reinforced PLA. So, what other materials can be done in PLA? Any idea? So, I have listed all the materials here. What do you think? Which material can be built in FDM? I have thermoplastics like PLA, ABS, PETG, PEEK, metals like titanium, stainless steel, ceramics. I have concrete, I have food material, I have hydrogel. So which one do you think can be printed in FDM? Okay, someone can suggest thermoplastics, because till now most of the research is done in thermoplastics. Do you think other materials can be printed in FDM? It's a yes or no question. So we can answer both yes or no. Do you think these materials can be printed in FDM? Yes or no? Okay, I will ask in a different way. Yes, Aravind Dutt sir. Yes, yeah. All these materials can be printed in FDM. So let me rephrase my question. Do you think only filaments can be printed in FDM? Okay, some may say that FDM is also known as triple F, that is fused filament forming, right? Fused filament fabrication, right? So in the name itself, that is filament. So let me ask my question like this. Do you think FDM can print using only filaments? Or I can have raw material in different format? Can it print only filament, or it can print any other form of material? No. Yeah, actually it can print other materials also. You can actually have a paste type of raw material. In order to print food materials, you can have paste. Only on the thermoplastics, okay, like APLA, ABS, PETG, nylon, PEI. So apart from this thermoplastics, we can also have a different classes of materials being printed in FDM. Okay, so the printer will be, you have to choose the printer according to the material type. Yeah. So most of the research, most of us will be, if you are using FDM, most of us will be working on PLA only, because the PLA is easily printable. It doesn't require much temperature. So even a desktop printer which has up to 300 degrees Celsius, that can be used. But when you go down down this domain, like if you focus on PLA, PETG, ABS, nylon, these can be printed using a normal desktop printer. But if you want to print PEI, commonly known as Ultim material, or if you want to print PEEK, then we actually require industrial FDMs where the temperature can reach up to 500 degrees Celsius. And we also required a specialized bed. Okay, the bed should be heated. You have to specifically heat the bed, and it should be in a closed environment to print those bodies. Okay, let me start with ABS. So printing ABS in a desktop printer it's viable, but what the problem is, it will also produce terrain fumes. So you should you should have a good exhaust systems. And another thing is the ABS will not stick on the paper bed properly. Okay, once you print it, it will stick on. When you move on to the next layer, it will start to come off. So for printing ABS, you should actually have a glue stick. You should have a glue stick, add the glue stick onto the bed, and then only you need to start to print the ABS. That is the difficulty you will face. Whereas in case of nylon, you should have a heated bed and enclosed bed. Okay, then only you can have a good nylon print. So these are the difficulties that you will face while printing thermoplastics. So PLA is very, very easy to print. PLA, the carbon fiber reinforced PLA or a glass fiber reinforced PLA. If you have a good nozzle, like a hardened steel nozzle with 0.4 mm diameter, you can actually print the carbon fiber or a glass fiber reinforced PLA. But in order to print a PEEK or PEI, because these thermoplastics, these only can actually replace metals like aluminum, etc. in aerospace applications. So if you want to print PEEK and PEI, then you should move on to an industrial FDM printer, or you should have a suitable modifications in your desktop printer so that it can accommodate printing PEEK or PEI, because we require very high nozzle temperature. You require up to 400 degrees Celsius, then only it can be used. The biggest advantage of PEEK is it is biocompatible. So if you are working on any implants or scaffolds, then PEEK is your targeted biocompatible thermoplastic. Yeah, so I want to give a glimpse about PEI, because if anyone is going to choose aerospace sector, then PEI is your it's your ideal thermoplastic, because they are flight approof, they are flame resistant, they are actually chemical resistant, so lightweight, and they can be FDM printed. So these characteristics makes PEI a better class for your aerospace applications. For example, Airbus are actually reduced their cabin size by changing from aluminum air duct to the Ultem air duct. So here they have actually reduced to 140 parts. The air duct, which initially had 140 parts, to just a 16 part. So you can easily print it and you can easily assemble it. Similarly, in robotics, end of arm tooling. If your robot, these are all arm toolings in your robots. That is at the end, if you want to pick or if you want to place it. So these kind of end of arm tooling, these were initially printed using aluminum. Now they have shifted to the Ultem because of its low weight and high strength combination. Right. So my second focus, I was talking about the materials, engineering materials. You can actually try to use different engineering materials into FDM and see what type of characterization they list. That is, what is the mechanical strength, what is the advantage and what is the drawback in printing that FDM components. You can analyze in that way. The third focus is, it is a medical field, patient-specific application of urea. It's a huge sector. Okay, as I was saying, it is a very, very huge sector. You can actually focus on your research on this. You can actually make a patient-specific cutting guide or a surgical scalpel or an implant or a scaffold or a drug delivery devices. We will see each in detail. Yeah, this is one example. So this is a military built surgical kit. On-site, they have taken the 3D printer and they have actually built the kit consisting of scalpel handles, retractor, needle, hemostat. Okay, all of them were built using ABS. Okay, these are just the handles. In that handle, they were actually inserting with the stainless steel knives. Okay, the cutting part will be done by steel only. These are the handles that have been, depending upon the demand, they are actually printed in. Yeah, so I was talking about cutting guides, right? So just imagine in our industries, we will be having jigs and fixtures to manufacture any particular mass-produced components, right? So similar to jigs and fixture, in medical field, we'll be having a cutting guide. So the cutting guide will be used to perform complicated operations. For example, look at this particular operation. Okay, so there is a bone defect here, and I have to do an operation, right? So what I have to do is I have to cut in this part, and I have to insert 2 screws in this part. Okay, so I know what are the procedure to be done. Okay, so cut at this bone and insert 2 screws in this bone. So depending upon that patient's CT scan, I can export that particular bone. Okay, using that particular bone, I can design my cutting guide. Okay, so this cutting guide is made up of PLA. See, I have to just place this cutting guide onto the bone. Okay, you're performing a surgery, you are cutting it through the flesh, and you have reached that bone segment. Place the cutting guide onto the bone. Okay, so wherever the cut, so it is showing here, right? Cut here, then insert 2 screws in this part. Okay, so cutting guide, it is actually patient specific, so it's of one-time use. So you don't require any complicated cuts, because if you're going to use it multiple times, what happens is it should pass through the sterilization process. Okay, sterilization cycle. So these thermoplastics, it might be difficult to pass through the sterilization cycles. So this is a one-time product. So you can actually use PLA, high temperature PLA or nylon. Okay, so this particular journal, they have actually compared the effect of all these 3 material for cutting guide. Okay, so let me explain how they would have started. So you have the CT scan. Okay, you have the CT scan of the bone of the patient. Okay, so from that CT scan DIPCOM image, you can convert that into a CAD model using this Invisalius software. Okay, you can use Invisalius or 3D Slicer. Okay, these 2 are free software, open source software. Anyone can use it, or you can also use Mimic. It is very, very beautiful software, but it is a paid version. But the features of this software is also available in Invisalius or 3D Slicer. Okay. Once you have that CAD model of the patient, you can know what is the length, width, or whatever the surface profile, okay, contour profile. Depending on contour profile, you know where the cut has to be made and where the screws has to be inserted. So you can actually build in a CAD model of the guide. Okay, you should know where it should be attached, where it should be cut. Okay, it can be easily done. Then it can be converted into a CAD model. Just a second. Okay, this is one important research domain in biomedical. Whenever you're making a complicated surgery, we don't want to have a revision surgery. It gives the surgeons a practicing environment. Okay, they can also have the practice. They know that this particular bone has been damaged, so this cutting guide will actually fit correctly because it has been built patient specific. Okay, that is one important field. The second one is implant, right? So if you have anyone in your home above 60 years, they would have undergone a hip surgery, either left or right. They would have undergone at least a hip or knee surgeries, right? Because in India, the demand for the hip and knee surgeries is very high. But the thing is, it is very costly process. It costs around 5 to 6 lakhs. And in this 6 lakh, 26% of the cost is because of the implant. Because in this implant, the material will be either titanium, or it will be titanium or any metal like stainless steel, cobalt, or chromium alloy. Okay, so they are very costly. So if you are able to replace this metal by any other polymer, then it will be going to be a huge achievement. Yeah. The problem with the metal implant is they have a very, very higher young modulus. That is, when you compare the young modulus of the implant, metal implant, with that of the bone implant, it will be 10 times higher. For example, titanium, it's the Young's modulus is 100 gigapascal, but your bone stiffness is only 10 gigapascal. So if you are going to use a polymer like PLA, whose Young's modulus, it will be around say 3 or 4 only. So that case, it will be similar to the bone material. Okay, so what's the problem here is, when I use titanium implant, most of the stress will be acting on the titanium. Okay, so the bone around that implant, it will get weaker. Okay, stress reduction happens, and what happens is the bone around that implant, it starts to not perform its function. Okay, this is actually known as stress shielding effect. Okay, so that will result in failure of the implant. So you have to do revision surgery. So this implant will work only for 10 years. And after 10 years, you have to do revision surgery to make it work better. So this is where we are going to replace the metal implant with the polymer implant. Okay, I will show you one example. So this is a peak polymer implant. Yeah. So you are actually using a polymer implant in this case to perform the defects, to have to overcome the defects. Okay, let me show you one video. Wait, I'll just explain it instead of video. I'll just explain what is happening here. So actually this implant is being topology optimized and we have used lattice configurations. I will tell you what is topology optimization. Check out this bracket. Okay, this is a wall bracket, simple wall bracket. It is completely solid, right? Now check out the end result here. Okay, so this is actually topology optimized. What they have done is they have removed the solid material in this bracket and they have kept the material only where the stress is needed. Okay, so what they have done is this solid bracket, they have taken this design and what they have done is they have they did a stress analysis and they determined where actually stress will be distributed based on your given loading conditions, and only in those areas they have kept the material. In remaining areas, they actually removed the material. So this is the final result. Okay. So whatever application they have developed this solid bracket for that application, this optimized design is going to work. Okay. That is known as topology optimization. So you have a generative answer software. We show you that generative answer software which can perform that one. Let me play this video. Look into it. This is a generative design software in ANSYS. So they have created a wheel that is a cast wheel. Okay, so they are going to apply the loads depending upon the application. They have an idea of whatever loads that is going to act here. So they are actually once designed, they are applying the loading conditions. These are the loading conditions. Okay, so they have shown the positions where to apply the load. So once they have done the analysis, once they have pointed what are the loads that are going to act, they are going to run. Okay, yeah. So they have what they have done is they have imported that geometry into the ANSYS generative design. They have specified where the loads is going to act. Then they have simulated it. So the end result is you have these many possibilities. Okay. So each of the possibility will work for that particular application. Do you think this can be built using a traditional manufacturing process? No. The additive manufacturing process has given path for constructing these. Okay, these kind of brackets, they will have a reduced volume, right? Reduced material, reduced waste. Okay, you can use this instead of the solid one which was shown in the beginning. Okay, let me show. Okay, so these are some of the examples of topology optimization. You can easily do this in SolidWorks, or if you're okay with the ANSYS, you can also use ANSYS generative design. So finally, they have taken up this particular model. So this strength-wise, this is equivalent to the initial solid wheel they had shown. Okay, so that is about topology optimization. So why I'm talking about topology optimization, I will show you how we use topology optimization and lattice optimization in our research to build a biocompatible implant. Yeah, about lattice optimization. So instead of having entire solid profile, okay, we are going to replace that solid profile using a unit cell, using a lattice cell. That unit cell can be a cube, or it can be a triangle, or it can be a gyroid structure, or it can be a quartz primitive structure. Okay, just imagine a honeycomb mesh, right? Instead of having a normal triangular mesh, when you go with a honeycomb mesh, you will be having a better stiffness. Okay, better stiffness with higher strength, right? So instead of having a traditional solid implant, what we are going to do is we are going to replace this implant with different lattice structures. Whichever lattice structure will work for that particular application, we are going to select that particular lattice structure and use it. Okay. Another advantage of using this lattice structure instead of solid structure is this lattice structure will promote the growth of the cells inside the implant. Okay. So I have told you two important drawbacks of using a traditional metal implant. The one is there will be lot of stress loading onto the implant, which makes the bone around that particular implant to fade. Okay, so you need to have a revision surgery, say for example after 10 years to remove that failed implant. That is one reason. Second one is when you have a solid implant, it is not going to promote adhesion of cell onto that particular implant. But if you have a porous implant, the cell will grow inside it, and you will be having a better long-term implant. Okay, so inspired by these ideas, what we did is we actually did lattice and topology optimization of implant. Our problem is, so this is a CT scan of a normal patient, a CT scan of the vertebral spine. Okay, this is a spinal implant. This is a spinal CT scan. So what we assume that this part has become defect because of some cancer. Okay, some cancer has eroded this particular profile. Okay, so we actually removed the T4, T5, and T6 thoracic region. Okay, so we have the remaining region. So we removed this. Okay, this was done using the 3D slicer software. So this was the patient's spinal cord after removing the T4, T5, and T6 segment. So each patient will be different, right? Each thumb fingerprint is different. So each patient data will be different. Also, when a particular bone breaks, the break segment, it will be very, very different because it is each break segment will be different, patient specific. Okay, this curvature, everything will be patient specific. So we have imported that particular data, and now we have taken that into the CAD model. So we need to build an implant that fills this region, right? So we taken up 4 different structures. We have unit cells, right? We had gyroid cells. We have a hexagon profile. We had the triangular profile. We had the 4 different lattice structures. So we tried building 4 different lattice structures, and we checked the numerical results. Which lattice structure had better mechanical strength and stiffness as compared to the bone structure. Okay. We then finalized on the hexagon structure, and after finalizing that, we did topology optimization. We didn't want to build a implant in this profile. Okay, we wanted to further reduce the weight of that particular implant to make it more stronger, right? So we did topology optimization. We applied what are the loads that are going to act on the vertebra. Like we applied the compression, we applied the flexion, we had axial rotation. So those kind of applications we did, and we finally generated this topology optimized profile. Okay, so you can see this is completely a circle profile, right? After fitting into the spinal cord obtained from the CT scan data, you can see the curvature has changed. This is patient specific. So that is where the patient specific implants can be done. So fitting this into a patient, it will create a lot of problem because it won't be a perfect fit. Whereas this fit, so this is how the patient's curvature of spinal is available, right? So this will perfectly fit and it will easily promote cell addition and the cell other proliferations. So this was a final implant. This was a PLA material, plain PLA material. It is biocompatible and this implant is enough to sustain whatever function the spinal profile can make. This implant is suitable when compared with the titanium or cobalt or stainless steel implant. So that was our result. So this was also a good work, and we actually published this work. We actually took the CT scan data, converted the TIPCOM image. This was the profile. We compared 5 different lattice structures. We had gyroid, schimates, primitive, hexagon, rectangular, and triangular. Out of all these 5 data, hexagon proved to be better structure. So that was done using a static analysis and under axial compression. We did numerical analysis and we found that hexagon structure provided better support for this implant. So we choose this lattice structure. Then we place this lattice structure in the spinal cord, corrected the curvature profile. Then we performed the topology optimization. We applied axial compression, axial rotation, flexion extension moment, lateral bending moment. These forces and moments are the common thing that will act in a spinal cord. Okay, and finally we built a prototype, and that was then printed. Okay. In addition to that, we wanted to further enhance our research. So what we did is we did a FDM process parameter optimization. So this can be done using Optimatter. Optimatter is a very good software where if you specify the material type, it will actually optimize your process parameters starting from nozzle temperature to print speed. Okay, you can choose the optimal combination. So we did some 9 trials so that we can maximize our compressive strength, and finally we had a perfect implant that is in rival to the metal implant. So this was our work. So in our work, we were very clear. We wanted to do lattice optimization, topology optimization, and FEM process parameter optimization, so that your research has higher probability of getting published. Right. So we have seen biocompatible implants and cutting guide. The third one I want to talk about is scaffold. Have you heard this term scaffold? Can you tell if scaffold is different from implant? What is scaffold and what is implant? Any idea? Okay, implant will be staying inside the body; it will not decompose. Whereas scaffold, it is just for a temporary time being. Say, for example, your bone needs supports, but after the bone has regenerated, you want the scaffold to decompose. Then you can use scaffold. Okay, implant will be permanently fixed, whereas scaffold will just promote the cell addition and cell growth rate. And once it has done, it will automatically degrade. So mostly the scaffold had its origin in dental industry, where you'll be preparing the site. Okay, so this is where the teeth has been removed. So this area is actually hollow. You want to promote cell growth here. So what they will do is they will prepare this site for implant insertion. So once this site has healed and the cell has promoted, then they will insert the implant. So for this promotion only, we will be using scaffolds. We have various types of scaffolds, natural and synthetic. So this is a bio-inspired scaffold. Okay. So instead of having just a solid scaffold, you can have a porous scaffold. Not any porous profile. Generally, scaffold material are made up of calcium. Okay. So what in this research they have done is they are focused on the atomic structure of HAP. Okay. Atomic structure of HAP, that is the atomic structure of HAP and calcium. Okay, so HAP atomic structure had hexagon channels. Okay, lot of hexagon channels can be seen from the microstructure or atomic configuration of hydroxyapatite. Okay, and in case of calcium, you can see lot of triangular channels. So this research tried to produce a scaffold that has both the hexagon and triangular channels. Okay, so the front view you can see lot of hexagon channels, and in the lateral profile, that is in the side view or the top view, they had the triangular profile. So once they had this type of lattice structure, they actually fabricated the scaffold using this lattice structure, which had very much similar mapping to the bone structure. So it was very much similar to the bone properties. So it easily promoted the cell addition and proliferation. Yeah. So I was talking about profiles of scaffolds made up of calcium and hydroxyapatite. So how to build that? So I was saying that FDM not only is restrained to the filament usage, right? So instead of filament usage, here you are going to use a paste. Okay, every 3D, you would have heard the term bioplotter, right? Bioplotter will be very, very costly because the bioplotter will be using pneumatic controlled extrusion, right? So here, instead of having a nozzle, what they have done is they have replaced the nozzle with the cartridge, a cylinder portion, right? And the cylinder portion, the end portion of the cylinder has a syringe, right? So you will be using these hydroxyapatite and calcium composition that will be held in this cylinder, and the petri dish, over the petri dish, you will be moving the syringe to create a required domain, required profile. So this is how the FDM will be modified to make it as a 3D bioplotter. So this is actually the bioplotter. So you will be having lots of multiple cartridges, and each of the cartridges will be pneumatically controlled. Whereas this modified bioplotter, it requires stepper motor only. It is basically a FDM printer. Instead of having a nozzle and extrusion chamber, you have a cartridge containing the hydroxyapatite and calcium material, and instead of having a nozzle, it's having a cylinder. It is having a needle which will be placing the scaffold material step by step, layer by layer. Romati Shankar sir, can you please mute? I think I have accidentally unmuted. Yeah. So the biggest thing about bioplotter is the scaffold once produced, it won't stop at day one. Okay. Since you are actually building it with live cell culture. So day one, there will be a few live cells. Day 5, it should have to proliferate. It should actually stick to the scaffold and it will start to grow. So that is the biggest problem with the bioprinting. The cell culture with your injecting, it should not die and it should start proliferating. So using using this paste-based FDM printer, you can actually print live organs. Okay, till now there is no scientific evidence of organ being printed, but that is an industry that's a company known as Organova, where they actually printed some bio organs, but it is not being used on human. What they are doing is they are using it for medical industry, where they can run the test run on that particular bioorganisms. Instead of doing the test run on the live human, they are actually giving these. For example, they will print the tissues over which the medicine will be applied, and they will check whether this medicine is having any side effect or not. Okay. So that is what I'm talking about, the paste-based extruder. So in this cartridge, you can actually have the biocompatible, that is biocompatible scaffold material, and you can actually print it. So we actually made this nose. I'll show you that. We actually made this nose using RTV silicone. So this is actually not made for it was made for robotic anatomy, soft anatomy, robotics. We tried printing it, and after curing it, it was actually very much flexible. So we have a paste-based extruder. So in this paste-based extruder, we had RTV silicone, that is 7071 grade raw material. So this injection-based material, so this paste-based was extruded, okay, layer by layer, and then we built this one. So this one was our work. So similarly, you can actually build other kind of robot for the soft robotics and biomimetic structures. Okay, that is also a very good research domain. So they are actually building the robot, but they want that robot to look like a human. So they want to give a human-like structure to the robot. So for that, they are finding which material and which machine can 3D print according to the need. So that is also a good research area. The next one is drug delivery devices. Very, very fast-grown areas. So at what particular dosage a particular drug has to be delivered to the patients. Okay, generally we use tablets and capsules to give drugs, right? So this can be FDM printed. Just imagine any 65 or 70-year-old people, they will be taking up a lot of drugs. From morning they will be taking 3 medicines, afternoon they will be taking 4 tablets, right? Just imagine I'm going to take only 1 tablet, and that tablet will give all the required dosages of drugs taken throughout the day. Okay? That is the magic of FDM printed tablet. Okay, so that kind of tablet can be done. I'll show you. There are 4 types of release. Immediate release. As soon as you take the tablet, immediately the drug will be released. Okay, so for that you would be having a very porous-like structure. So this structure, when taken, it will immediately dissolve in your gastric acid and it will immediately release the drug. For sustained, you can have a higher infill density. So what happens is throughout the day, slowly it will start to digest, and at the end of the day, the dosage will be spiked. Chronic release. With the time, the profile will vary. Okay, so here the outer portion will be denser and the inside portion will be porous. Okay, so like that you can design your tablets patient specific. For example, this tablet, it has 4 drugs, right? So when you taken in the morning, immediately this green portion, green drug will be released. This sustained area, this will be released maybe in the afternoon. Okay, so you have to design the profile in such a way, you have to make sure that a single drug is enough to compensate all the different drugs you're going to take. This is also a very, very big upcoming area. So for that, you have to create a filament making machine. So they have used the hot melt extrusion. This machine is used to create this filament. So this is a hopper. Here you will be putting in the pellets. This is a polymer. Okay. In this polymer, you want to have your APIs. That is medicine, right? API is the medicine. So the medicine and the polymer pellet will be placed here. From the hopper, it will be heated, and then you will be getting the filament. During the heating process, you should make sure that the API is not changed or modified. That is the biggest challenge. Okay, so using different designs, so using different lattice design, you can actually create a suitable drug release mechanism. Yeah, this is one of recent work that is that actually attracted my attention, because I want to work on this one, because we recently bought in the paste-based extruder. So they have actually mixed a polymer, HPMC polymer, with the drug paracetamol, and they used HME to create the filament. So using various designs, see, so we have various designs, various lattice designs. They have actually created different drug release mechanisms. So sustained release and fast release. They have varied the weightage from 5 to 50% of paracetamol, and they have made the thermal and mechanical testing on the designed tablets, and they are also checked out the drug release modulations. So these type of research are actually currently gaining momentum. Yeah. So combine the scaffold with the drug delivery. Okay. So that is a bone defect, right? So you are going to create a scaffold which will degrade. Say, for example, it will stay there for 3 months. After 3 months, it will automatically disintegrate. After 3 months, this bone defect will be automatically repaired. Right now, imagine I have created this scaffold. This scaffold itself will release some antibiotic for faster recovery. So this is a very, very big domain. Okay, so they have actually used filament, right? Instead of filament, you can also use some paste-based raw material. So here they have actually created a scaffold with antibiotics. The filament has antibiotic as well as scaffold material. So this will